More horizontal circles. Put your phones away. You know who you are. One neat example of a horizontal circle would be artificial gravity. One method of generating artificial gravity in outer space would be to build a circular space station and spin it. So question A says, if this space station has a radius of 35 meters, what does the period of rotation need to be for an astronaut to experience 80% of Earth's gravitational field? In other words, 80% of a G. Well, I think I'm going to be using the equation with the t in it. And what path are we tracing out? A circle. I think this is a job for a... I'm going to do a free body diagram on the right hand, on the top view. So what are the forces acting on this person? Wait a minute. Are we in space? No gravity. Okay. What else? Elias, what? Sorry? I disagree. First of all, what path are we tracing out? What path are we tracing out? So where must there be an unbalanced force pointing toward the... I know there has to be a force that way. It's not gravity. What is it? Acceleration's not a force. What? There it is. The surface. There is a normal force. Even though there's no gravity, there is a normal force. In fact, if you want the equation for a space station, the normal force is what's pushing us in a circle. Oh, now it won't erase. Oops. Oh, there we go. For circular force, I'm going to use m, because they mentioned period, 4 pi squared r over t squared. I don't know the normal force. And I can't say, oh, but look, I know another force the same size as the normal force. Or can I? How big do we want the normal force to be according to part A? Read that, say that again out loud and proud.
80% of G.
0.8 mg. There, 80% of gravity. Oh, can little kids and grown-ups live on this space station? Why? What did this question want me to find? Which variable is that in my equation here? T. We're going to get the t by itself. Where is the t right now? On the... Wait a minute. Let's times it to the top on the other side. And let's move the 0.8 g to the bottom. I'll get this. T squared equals 4 pi squared r over 0.8 g. Oh, t squared? How do you get rid of a squared? Yeah. So if you're designing this space station, you need it to rotate every how many seconds? Let's crunch the numbers. It's going to be the square root of 4 pi squared, r was 35, divided by 0.8 times 9.8. I would encourage you to try typing this into your calculator again. Square root of that. I got 13.3. Yeah. So if we have this space station rotate once every 13.3 seconds, that will generate 80% of gravity. Period is measured in seconds. It's a time. Time to go around once. Would that work in real life? Kinda. There'd be a bit of an issue. 35 meters is not that big. Your height is around 2 meters-ish, a little bit less. That's enough of a fraction of that 35 that your head would experience a slightly different fake G than your toes. Your toes would experience the 80% of G, but your head might only be getting 77 or 76%, and that might be enough to make you just feel a bit weird. Maybe like you were almost always about to fall backwards. You might feel a bit nauseous until you got used to it, but you would get used to it after a few days. Let's continue living on this space station. Suppose the astronaut begins to climb a ladder that leads to the center of the space station. At what radius will the astronaut feel 30% of his or her weight? Will they feel lighter as they climb towards the center? I think so. So we have the same situation, the same free body diagram as before, where if we have the astronaut standing here, we have normal force is what's pushing us in a circle. On the right, it's going to be m4 pi squared r over t squared. And I'm using that one because the period of rotation will be the same. Remember when we opened class with the question about Tommy falling to the earth, we had Alex and Kieran and Braden on the merry-go-round. Even though Braden would be traveling slower, Kieran would be traveling a little bit faster, Alec would be traveling the fastest, it would still take you the same amount of time to go around once. Kieran doesn't rotate one less than you because you're all in a straight line with each other. So we're going to use this equation here, even though the radius changes, even though your speed changes, your period of rotation won't change. And I guess here we want 0.3 mg. M still cancel? What do they want me to get here by itself? Okay, how would I get the r by itself? How will I move the 4 pi squared over? Divide, how will I move the t squared over? So I think we're going to have the 0.3 g staying where it is, the t squared getting tacked on, divided by the 4, and the pi squared equals r, or do you mind? I'm going to put r equals here. Oh, and no need to square root this time. So that's going to be 0.3 times 9.8 times, I'm going to write 13.3, but I still have this number on my calculator, squared. So I'm going to use my answer button, over 4 pi squared. See if you get what I got. What'd you get? Yeah. In fact, you use your answer button because you initially multiplied by a pi squared, now you're dividing by a pi squared. You get a nice non-yucky answer, 13.125 even. So 13.1 meters. What was the original diameter? Or sorry, original radius of the space station? Where are we right now? 13.1. As we continue to climb, what would happen to fake gravity? Or What will the force of gravity be at the center of the space station? 0. There would be a little tube of weightlessness right dead center. If you were doing a big space station with like several thousand people, you might turn that part of that into a little recreation area. Or you might have an area just off dead center where G instead of 9.8 was maybe 0.2. And that might be a small enough gravity that you could strap fake wings onto your arms and flap your arms and fly like a bird. And you might turn that into a little recreation area. You could do some neat stuff. If we do ever build large spinning city-sized space stations, there's some neat stuff that we could do. I like example 2. I like example 2. Example 2 is a nice question. If you haven't figured out by now, if I cover an amusement park ride, I like this question, I like this question, I like this question. So roller coasters we've talked about. Okay. The Gravitron. What's the Gravitron? That's the ride that spins in a circle, and then there's 2 versions. In one version, the floor drops away. In the other version, you're tilted vertical. So I've been on the one where the floor drops away. The Gravitron spins its riders around in a circle. If the ride has a radius of 4.8 meters and it rotates every 2.5 seconds, what's the minimum coefficient of friction required between the riders and the wall of the ride? Diego, what's this question asking me to find? What's the minimum?
Coefficient.
Hey, what's mu? I don't know. What's mu with you? Okay. Any suggestions on what this might be a good job for? Yeah. So here's our rider. What are the forces acting on this rider? Get the obvious one. And we're back on Earth, so there is mg, yes? Are they sliding down the wall? No. Are they sliding up the wall? So I know there has to be a force the same size as mg that way. Not quite sure what force that is yet. What else? What path is this rider tracing out? So where must there be an unbalanced force pointing? What force is that? It's not friction. F? Nope. I'll give you a hint. This is the same physics as the space station. What? Yeah. Normal force is what's pushing you around in a circle. By the way, the fact that there's a normal force inwards, does that give you an idea of what the force pointing up might be? Yes. A little weird. Well, you can kind of imagine that we've, instead of the ground being flat, we've tilted the ground. And so now the normal force is pointing in the way we're used to, and friction is pointing in the way we're used to. Okay. What did this question want me to find? Okay. Vertically, are we accelerating down? No. Are we accelerating up? No. So vertically, it's a tie. Vertically, I can say friction equals mg. Vertically, I can say mu times the normal force equals mg. Is the normal force equal to mg here? No, it's not even in the same direction. I don't know the normal force. Or do I? What path are we tracing out? So I'm going to leave this equation, and now I'm going to write a horizontal equation. Normal force is what's pushing me in a circle. Which version of A am I going to use? The one with the V in it or the one with the T in it? Read the question and figure it out. Sorry? T, because they gave me the period, 2.5 seconds. So next line, I'm going to write m4 pi squared r over t squared. That's the normal force. Now I'm going to rewind time back to this equation again. I don't know the normal force. Oh, but look. I know another force the same size as the normal force, not mg. m4 pi squared r over t squared. So I'm going to replace the fn with m4 pi squared r over t squared. The mu is going to drop down like a domino in front of it. I'll get mu m4 pi squared r over t squared. That equals mg. Oh! Can little kids and grown-ups go on this ride? Yeah? How come? That's good. As far as I'm concerned, for the gravitron, there are three variables: the period, the radius, and mu. As far as I'm concerned, if I give you any two of them, you can find the third one. The key idea is to realize normal force is not equal to mg. Normal force is what's pushing me in a circle. Friction equals mg. And from those two, I can mix and match and find whatever I need. What this one wants me to find, Diego, what? What did this want me to find? Mu. I'll get the mu by itself. So how will I move the 4 pi squared r over? They're multiplying, so divide. How will the t squared over? Time. Are you starting to see, by the way, why I taught you the formula manipulation thing last year? Because to try and explain this to you otherwise, but you can just derive it on the fly now. Good. I'm very proud of the way you all bought into this. Mu is going to be g t squared all over 4 pi squared r. Mu is going to be 9.8. What was the period? Every what? 2.5 squared. All over 4 pi squared. What was the radius of the gravitron? 4.8. Pi squared times 4.8. Now I get a mu of 0.323. Probably the coefficient of friction on the ride would be larger than that, safety margin. But as long as you're wearing clothing and leaning back against a fabric that isn't very slippery, this ride will work. If you've ever been on the Gravitron, by the way, what you're leaning against, it's kind of this bumpy fabric texture, and I think that's all designed to just make sure the coefficient of friction has a healthy safety margin. Could they make the Gravitron out of ice? Wouldn't work. No matter how fast they spun it, you'd slide down if it was ice that had no coefficient of friction. Cool. Kieran, what does B want me to find? Speed. Oh, is there an equation for circular speed in this unit on your formula sheet? There is. No. Is there an equation for centripetal speed on your formula sheet for this unit? There is. What? Kieran, what? V equals 2 pi r over the period. Did they give me the radius? Did they give me the period? How fast are we moving around on the outside of this circle? 2 pi 4.8 divided by 2.5. We're moving at 12.1 meters per second. Okay. The other thing I could have done, Kieran, instead of giving you the period in part A, I could have given you the speed. And so instead of m4 pi squared r over t squared, you would have used mv squared over r. But then you could have walked over here and I could have asked you to use this equation to find the period, because you would know the speed and the radius. Fair enough? Cross out C. I skipped frequency in this unit. But I do have a picture, I think, somewhere. Let's see, where is it, Mr. Duick? Probably in here. Is this it? There you go. Can I make it larger? How do I zoom in? Zoom in. All right. There's how you can ride the Gravitron. Although he would be feeling a very different G on his head versus his feet. So you'd have to get used to it a little bit. You can ride it that way. I would love to. Playland doesn't always have the Gravitron open at the Playland Physics Field Day, because actually the P&E owns the Gravitron ride. But a few years ago, because the roller coaster was closed, they brought the Gravitron in its place. That was finally, I'd never been on it until then. I would love to go on the Gravitron with a box of tennis balls, have a student on the other side, and I would love to try playing catch while that thing was moving. And you would see that Coriolis effect that I talked about at the beginning of class, very large. And also, someone off to my left, maybe 3 spaces down, would also get pelted in the face by tennis balls, which would be a win for a completely different reason as well, right? I'm going to skip example 3. Going to skip example 4. Your homework number 1, number 2, number 3, four, 5. You can skip 6. You can skip 7. You can skip 8. You can skip 9. You can skip 10. You can also skip number 11, Nicole. 12 is kind of okay. And 13 is good. Put your pencils down, look up.